Relative velocity. You must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. While the train must be traveling faster than you to be able to pass you, it does seem slower to you than it would be to someone standing on the ground and watching both the trains. In case both the trains have the same velocity with respect to the ground, then to you the other train would be seen to be not moving at all. To understand such observations, we now introduce the concept of relative velocity. Consider two objects A and B moving uniformly with average velocities VA and VB in one dimension, say along x-axis. Unless otherwise specified, the velocities mentioned in this chapter are measured with reference to the ground. If xa of 0 and xb of 0 are positions of objects A and B respectively at time t equals 0, their positions xa at t and xb of t at time t are given by xa at t equals xa at 0 plus va into t, xb at t equals xb at 0 plus vb into t. Then the displacement from object A to object B is given by xba of t equals xb of t minus xa of t, which equals xb of 0 minus xa of 0 plus vb minus va into t. Equation 3.13 is easily interpreted. It tells us that as seen from object A, object B has velocity Vb minus Va because the displacement from A to B changes steadily by the amount Vb minus Va in each unit of time. We say that the velocity of object B relative to object A is Vb minus Va. Vba equals Vb minus Va. Similarly, velocity of object A relative to object B is Vab equals Va minus Vb. Figure 3.16 Position time graphs of two objects with equal velocities. This shows Vba equals minus of Vab. Now we consider some special cases. A. If Vb equals Va, Vb minus Va equals 0, then equation 3.13 xb of t minus xa of t equals xb of 0 minus xa of 0. Therefore, the two objects stay at constant distance xb of 0 minus xa of 0 apart, and their position time graphs are straight lines parallel to each other as shown in figure 3.16. The relative velocity Vab or Vba is 0 in this case. B. If Va is greater than Vb, Vb minus Va is negative. One graph is steeper than the other. Then they meet at a common point. For example, suppose Va equals 20 meter per second and xa of 0 equals 10 meter and Vb equals 10 meter per second and xb of 0 equals 40 meter. Then the time at which they meet is t equals 3 seconds. Figure 3.17. At this instant, they are both at the position xa of t equals xb of t equals 70 meter. Thus, object A overtakes object B at this time. In this case, Vba equals 10 meter per second minus 20 meter per second, which equals minus 10 meter per second, which equals minus Vab. C. Suppose Va and Vb are of opposite signs. For example, if in the above example, object A is moving with 20 meter per second starting at xa of 0 equals 10 meter and object B is moving with minus 10 meter per second starting at xb of 0 equals 40 meter, the two objects meet at t equals 1 second. Figure 3.18. The velocity of B relative to A, Vba equals minus 10 minus 20 meter per second, which equals minus 30 meter per second, equals minus Vab. In this case, the magnitude of Vba or Vab equals 30 meter per second is greater than the magnitude of velocity of A or that of B. If the objects under consideration are two trains, then for a person sitting on either of the two, the other train seems to go very fast. Note that equation 3.14 are valid even if Va and Vb represent instantaneous velocities. Figure 3.17 Position time graphs of two objects with unequal velocities showing the time of the meeting. Figure 3.18 Position time graphs of two objects with velocities in opposite directions showing the time of meeting.